thank you everyone for coming. So I'm Nayara, and this is going to be a combined talk with Veronica that's there. And we are going to talk about generalization and similarity learning, and in particular about this phenomenon that's very intriguing, the double descent. We are going to tell you what is contrastive and similarity learning and what is double descent. And I realized that for this talk, I need a context slide because the audience, most of people are physicists. So my background and Veronica's background is in high energy physics, but this talk is actually not the natural direction, it's not applications in high energy physics. Well, I'm around TV, Veronica's a bit higher. But this talk is actually focused on understanding deep learning and machine learning phenomena. And people maybe call this broadly as machine learning theory. I like to call machine learning phenomenology, because right now we do not have the right tools, mathematical tools to study these objects. We can write down toy models and understand a lot of things, but to understand like things that really matter for the state of the art, we need to do FINU. We cannot do theory at the moment. There is no theory. And maybe you should ask, right? The 1 million question, why should we care about this? Well, maybe I can tell why I care about this. And there are two reasons. One reason is that I hope we will show you that there is a big gap in what we use and what we understand in deep learning. And this is what I want to stress, is that this goes much beyond like interpretability and explainability. It's much worse than this. Right? Basically, we do not have even good intuition about the statistic of these models. And of course, this is well known in the machine learning community, but maybe not so well known in science. And this is a problem for science, so it's a problem for scientists. But there are other reasons. The other reason is that the phenomenon itself is quite intriguing and it's very interesting. And I think as physicists, we're quite good at connecting theory and data. And in particular, many times, right? Not sometimes, but many times our models are not that rigorous, but they are still very useful. So I guess we can really help to fill this gap. Until we have a theory of deep learning, we can do some phenomenology of deep learning. Yes, so this is gonna be the plan. So we're going to give a long introduction on double descent. There are other weird phenomena like adversarial neural nets, adversarial attacks, but this is going to be the focus of this talk, the double descent. And then Veronica is going to take over and give you more details about this, like from concrete, we can really see these things analytically for some toy models. And then I'm back again. I'm going to discuss our work, how double descent appears in the context of similarity learning and contrastive learning. And the way it works, you just ask me the nice questions and leave all the hard questions to Veronica later. So that's okay. So we as physicists, we are told since early ages that more parameters is just something really bad. We should avoid, this is not elegant, this is disgusting, we should not do this. We want to write a theory for just an equation for one line. This is what we learn, right? And there is the famous quote by von Neumann, right? With 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. And apparently, people actually have done this in a paper. And then I took the slide from art. However, deep learning is not really much worried about what we physicists think is elegant, right? It's just highly over-parameterized. When I say over-parameterized, I mean just like you have much more parameters than data points. And just to give you some flavor of what we're going to discuss, the phenomenon that we're going to discuss later, here I took this from this review. So we want to fit this red dot points with ReLU networks. So you can just think about 2-layer networks. One layer is trainable, the other is fixed with random parameters. So it's really like a prototype of a neural net. And if I try to fit with 3 parameters, is the classical underfitting, right? This is really bad. In the middle, you just are in the, let's say, the standard overfitting, right? I'm trying to fit this 11 points with 30 parameters. This seems quite bad. But then I'm trying to fit now 11 points with 3,000 parameters. This is good again. This is smooth, right? I really do expect that if I put more points here, this generalizes well. This seems a good fit. And this is kind of intriguing, right? This seems really weird. Why this? Yes? But for now, I'm not giving you any measure. I'm just giving you like some intuition. I expect that if I'm generating more points with the, I didn't give you the true function, right? To say this, I need to give the true function that generate the red points. I'm just saying if I'm dropping new points, I do expect that they will be close to this curve, right? If I give you the true function, you can really just do mean square error and see, right? But for now, it's just, I just want to build the intuition until you get, we're gonna get there. But yeah, I'm go. Ah, I see what you mean. Yeah, it's just, yeah, I agree. Okay, so I'm going to discuss in this context here, it was just to give you like what's going on, right? Why this is what people observe in general in complicated neural nets, right? They increase a lot the number of parameters and things generalize better when I give a proper measure of generalization, right? Here, and just give you some intuition. And then what we could ask now, well, can you see this explicitly, right? For real neural nets that people are using in practice. And then I'm going to discuss these two papers, right? They are, let's say, classical papers in machine learning, like 2017 is a classical paper in machine learning. I have discussed first this understanding deep learning still requires, I think, generalization. This is actually a paper from 2017, but actually they put a new version of the paper, basically just changing the title with the still, because we still didn't figure out how to do this. And the second, I'm going to discuss the phenomenon itself, right? The beast, the empirical, overwhelming empirical observation that large models perform better, that people have been observing this for a while, but they give this name in this paper by Belk in 2019. Okay, so let's do an experiment. Maybe experimentalists will be like, this is not an experiment, but we really call this an experiment. So what I'm doing here, I take a data set with proper labels. And what I'm going to do, I'm going to completely randomize the labels, right? I mean, pizza here, they share a lot of features, but now pizza is dog and pizza is cat. I just completely randomize this data set uniformly among the classes. Let's assume like a 10 problem, a 10 class problem. And what I'm doing this because now this data has no structure. Basically, if I'm feeding a model with this data, I mean, Kosio is a bit upset. No, this is supposed to be very informal, so please interrupt me at any time. Okay, fair enough. Yeah, indeed. I'm gonna say so. This data has no structure, so in principle, if I'm giving you, let's say, test samples to this model that was trained with this data, I'm feeding noise, let's say, right? I'm just feeding noise because why they do this? Because now they have a way by construction that there is no generalization. That's why I'm building this experiment. So if I'm fitting completely this data, it means that my model memorized, right? My entire data set, because there is no structure, right? Dog and cat, they are similar. So I have just to memorize the whole thing. And then they applied this for a state-of-the-art neural nets at the time, right? 2017. We had, like, for instance, inception. So just to give you the idea of that time, right? 2017, this was the state of the art. And let's see what they see. So let's see first the learning curves, like learning curves just for training, the average loss as a function of the optimizer steps. And let's see the extreme cases, right? Let's see the true labels when I'm really training with the true labels, and then when I'm training with completely random labels. So if you train first with the true labels, you see that there is some structure. I converge to loss 0 very quick, right? It's easy to find a structure. I just can overfit this data set. Yeah. Gaussian, when they introduce some Gaussian noise, I mean, it's just, this is like intermediate regimes, right? Let's focus on the true and the roundable Gaussian, just some Gaussian noise that you could introduce. So then you see how it goes from one to another, but here would be important just the extreme cases. Okay, when you have true labels, you converge to loss 0. When you have like random labels, it takes more time, but eventually we're also going to completely explain, let's say, this data set. You get like loss 0. So there are two obvious observations that we can You can just by looking at this plot, we can say is that for random labels, there is no generalization by construction because I just built a data set that cannot generalize. Nevertheless, if I wait long enough, I still can overfit this data set. Fine. So in principle, there is nothing very much special about my model itself. It's just like I have so much capacity, I have so many parameters that I can just memorize my entire data set. Nothing special. So it just doesn't make sense to be arguing which model is better. You just like have so many parameters that just memorize the whole thing. The other thing is that you can now try to analyze the generalization error, the test error. So if I show completely new samples, what I expect, right? This is also intuitive, right? I have test error here as a function of the label corruption. If I have completely like zero label corruption, let's say I get what I expect, right? I mean, of course, for MLP is not so good, but I generalize well. This is test error, right? However, if I keep increasing my test error, eventually get just random, right? This is a 10 class problem, so 90% of error, 1 in 10. So I just get a random answer. This is what I also expect. Yes, sorry, I thought there was a question. No. Okay, so indeed, there is a big gap between training and test because my training is like zero loss. I basically get zero training loss, but test error is quite bad, right, in this sense. Okay, so then we can conclude two things from this. One, it's obvious, like deep neural nets can easily fit random labels. I can just put so many parameters, my model will just memorize the entire data set easily. But the thing that I found more interesting here is that now they construct an experiment where they can say clearly that optimization is different from generalization. Because by construction, I cannot generalize. Although every time we take a model, take a loss function, and try to minimize this with optimizer, we are doing an optimization procedure. But here, I optimize perfectly. My loss is zero, but I cannot generalize. So this is somehow when people tell you, oh, we're doing machine learning, this is just optimization problem, we can just say, okay, it's not. This is a proof, at least you can, this is okay. They went to the extreme case to prove that this is not the same thing. Of course, this is related, but optimization is different from generalization and doesn't mean that I have loss zero, that I generalize in a good way. And what they say in this paper, they conclude, right, also in the paper in the new version, that we still need some way to formalize these models, not only related to the architecture, right, with the model itself, but we need some way to combine algorithm data distribution to explain this over parameterized regime. And they finished this paper with a big question. Nobody knows how to do this at the moment. Okay, so now I move to the beast itself. There are some questions. Good. Okay, now I'm showing actually the true function, right, that we discussed at the beginning. So let's just suppose that now I'm trying to fit these samples, these blue dots. And here now I'm showing the true function, right? The orange and the model. Then I'm trying to fit in this first plane here with 1 degree, right? So this is quite bad. I don't expect this is going to generalize. I mean, the usual other fitting regime. In the middle, now I'm trying to fit with 4 degrees of freedom. This seems quite good fit, right? I do expect that if I'm generating new points with this true function, that they will be close to the blue curve. That's basically what I was telling before. Of course, now I'm in the classic overfitting regime in this last plane. So I'm basically going over all the points, right? And I have 15, trying to fit this with 15 degrees of freedom. I do not expect that if I generate new samples with the true function, that they'll be close to this blue. Classical, everything makes sense, life is good. And how, if you are into statistics, you probably call this the bias variance trade-off. If you're a physicist, you call this common sense, right? It's just how we do model selection. It's just what we do. We just have an error as a function of the parameters. So what we expect, right? If I'm increasing the number of parameters, my training error is going down until I'm basically going over all the points, right? I'm basically have training error 0. I'm memorizing my entire data set. However, I do expect that, I do expect that eventually I do not generalize anymore, right? At some point, there is a good point here, right? Where, of course, I should stop adding parameters in my model when this should be the perfect point. And okay, I should not keep adding parameters because otherwise I'm going to this regime, right? I'm in the overfitting regime. Everything good? This is the classical U-shaped generalization curve from statistical learning. However, so if you want to compare with what we just said here, I can just put, this is a model that's in this class here, right? In the underfitting regime. This is in the overfitting regime. And this is exactly the good model, right? The sweet spot that has exactly the complexity that minimizes my test error. Everything makes sense, life is good. However, deep learning is here, right? Deep learning is highly over-parameterized. Basically, they have at least one order of magnitude more parameters than data set, and they still generalize quite well. There is like overwhelming empirical evidence that if I increase this parameter, right, I have parameters, a ratio between parameters and the number of training data sets. If I increase this ratio, my test error goes down. This is like, every time you do, if you have already played with deep learning, you probably will have seen this many times. And what people start to argue what's going on, right? It seems just counting parameters is not a good measure of complexity. You have to do something else. This is not, of course, this function that's here that generalizes better should have somehow it's simpler for some measure than the other functions. And then people actually gave this name and they tried to reconcile this in this paper, right, by Belkin and collaborators. And what they said is that, well, actually this curve is not like this curve is this, right? Actually, what happened is that, well, machine learning practitioners, they are here, right? So they have not seen this peak. And what happens actually, we have a classical regime that what we study in classical statistical learning, and there is this modern regime where we actually cross this interpolation threshold that can be broadly defined as I just have enough parameters to completely memorize my entire data set. That's basically, yeah. No, in this case, here's just a cartoon, right? But okay, yeah, this is like a real. I can add regularizers that somehow Veronica gonna show, right? If you add regularizer, this can make like it not be so sharp like this, but does not disappear. Does not disappear. The effect is there. If you are in a nonlinear, it's a bit more technical because you need to be really nonlinear. But if I really nonlinear, you cannot make this disappear. Yeah, but you can. We are going to be able to see this like explicitly, right? With like analytically. And it's very intriguing, right? Because of course we will be able to see this in very simplified versions of the neural nets. But until now, okay, this is not quite long, right? 2019, but probably this paper has like 1,000 citations already. It's like a theory paper. And basically they point out, they give the name, right? This is happening. Let's try to understand this as a community. And there is no, good understanding for like complicated models and the range of validity. This is still an open question, right? We still don't know exactly why this happens and what kind of regularization, why the network is doing to find better solutions in this over.
It's here. Okay.
Yeah.
So, this looks interesting because usually people say if you over parameterize, then you can forget about it. There's no longer predictive. You can no longer predict things. So on how many things has this been tested? Is it model specific? It looks like, if you have one paper, you cannot test all possible setups in the world, right? So it can be a very specific feature of a certain subclass of tested
I see.
learning
You mean like
algorithms and so on. Now, you cannot, you can never make a general statement unless you have proven it somehow, right? So it could be that it looks like this for whatever has been presented in this paper, but if you look at other papers or other models which have not been investigated, the error goes up.
You mean like you never know when? Yeah, this is okay. I can say for some simplified models, for instance, like handle Fourier features, I know exactly when this point happens. Like when number of parameters is equal to the number of data points. This is like, yeah, you know exactly how to calculate. If you go to deep learning, you already don't know anymore. And this is not just intriguing from the point of view of theory, like, right? It would be nice to know when this gets better, right? Because then I can just train exactly at the right point. I don't keep trying to find where is the good point to train my model, right? I can just go to the right point.
Yeah,
but indeed, for some simplified models, I know we just calculated, right? Just the inverse of some eigenvalue. You can really see that when this blows.
But I mean, naively, I would say if I have a 2-parameter model, let's say, and I try to fit it with 1,000 parameters, I mean, it doesn't really make sense, right?
No, I agree. No, in this case,
yeah. Okay.
Do you want to say something? No. Yeah, that's okay.
Yeah.
Yeah, there will be like this would be okay. I'm showing you some experimental plots. These are really experimental plots, but I'm not explaining, right? This is like a 2 fully connected neural nets in this paper, but Veronica is going to go into more detail on this part.
It's important to point out this is related to the type of fitting. I mean, physicists will often think the fitting is neutral. This is fitting as related to back propagation in a deep network in this very, specific part of the zoo.
Yeah, it's gradient descent based, right?
Yeah.
Always gradient descent based.
But although people have studied in even the linear regression case, that weird effects still happen. I mean,
we're going to see linear regression. Exactly.
That's kind of about the. Okay, you're going to talk about that. Okay, I won't spoil it then. Okay.
I mean, sorry. The second question is, I mean, these plots on the top right, are you always the number of fitting parameters below the number of free parameters or not? No. You said the dashed line is where they meet. Basically.
Here, I have more at this point here. This cartoon is saying just like I have more parameters than data points in this modern regime. I just have more parameters than data points. And what to expect? What in principle before we didn't have like computational power to see, right? What we're doing before, right? Before, let's say, deep learning era, we stopped the training here, and this was going up, and everything makes sense. We stopped the training, right? Just because, of course, I'm overfitting. But then I don't know, machine learning practitioners, they just that's training here.
Yeah.
And then people from, let's say, classical statistical learning say this is wrong, this cannot work. Exactly. But they say, okay, we train and it's better. And then these guys here, like theorists, they actually indeed, okay, let's see what's going on. And they go like, okay, increasing like step by step, and they could, really be able to see this peak. And then we also, this is very robust. Everything you do, you see this peak. We also be able to see like.
Because I mean, honestly, in a lot of applications, I see people say exactly this. They say we stop at some point because afterwards it's useless and we have too many free parameters. And so
this is for sure the intuition. I'm saying like the intuition doesn't work here.
It's very specific models you were talking about. Yes.
Look at the loss.
Yeah, this is bizarre. Yeah, Veronica is gonna show a plot that I think it's very impressive. The one by Pritun et al, right? The one the deep learning. Yeah, the deep learning. I guess the first plot, and because I think it's very impressive because in this plot, this is a cartoon, right? But she's gonna show you like an experimental plot, and there you see that really the sweet spot actually is worse. I mean, so in principle, if you keep training, it's good. You just keep training, you're gonna get better than the sweet spot. And for a physicist, you say this cannot work, yeah. Indeed. Exactly.
Just to mention one thing, you keep saying if you keep training, but this is not the number of epochs.
No, you're right. Totally right. Yeah, you're just adding more parameters and then you train again with the same procedure. But there is also epoch-wise double descent, which is even worse. We also, I'm sorry, because this is because, yeah, there is this. After this paper, of course, a lot of people start to, okay, what's going on here? And some people found out this epoch-wise double descent. That's totally against the intuition again, because what you see, you start overfit, you should stop training. Early stopping is what we learn, right? I should not keep training because I'm already overfitting. Keep training. If you keep training, your curve goes down again. And we also saw this in our experiments. This one, we're like, this cannot work. This doesn't until you do it. But then you need a cluster, right? That's the thing. But yeah, this is the reaction, exactly the reaction that I expect. I mean, because this is weird, indeed. I mean, you should. One question? Okay. Indeed. Okay, so that's it. So now Veronica is gonna explain everything that I didn't.
Okay, yes. So I'm actually just doing a cameo here. Because of course, I mean, as Nayara was saying, this is exactly the reaction you hope to get, because otherwise this means that people are sleeping if they are not confused about what is happening. And indeed, the point is I mean, before we were seeing this kind of, not this one, but okay, this kind of thing, this is a cartoon, but this actually happens in real situation. And for instance, you know, standard data set CFAR, you study it with ResNet and so on and so forth, and you try to perform this experiment. So you fix the number of training epochs to, do not know, a few Ks, okay, just to be sure that you reached I mean, you train model till convergence. I mean, 4K epochs is a decent amount of epochs, so that you're actually pretty sure. And this is exactly what happens. So this is exactly similar to the cartoon we were seeing before, right? And the most I don't know, but surprising thing is that in this regime here is not that, I mean, you're just increasing the number of parameters. The model is still seeing the same amount of data, and anyway, it's getting better. And in certain situation, because I mean, when you start studying how your model generalizes, I mean, it's a little bit misleading, right? To say, oh, but look, the test error is going down. You look at generalization. So you should actually look not at the test error. You should look at the difference between the test error and the training error, right? Otherwise, it's misleading, but it may actually happen. I mean, not of course, not here. Here it's just surprising that the test error goes down. But the point is that you should keep an eye on the difference between the test error and the training error. And it may actually happen that in this super over-parameterized regime, the generalization error is actually better. But is this phenomenon super surprising? Well, there is something pretty similar happening in linear regression. The point is that in linear regression, you cannot have, let's say, you cannot have as many parameters as you want, right? Because the point is that the number, if you're doing a linear regression, the number of parameters you're actually using is actually the same as the dimension of your input data. But something similar happens here as well. It's just that you cannot over-parameterize the thing as much as you want, but then you need to start looking at the ratio between the number of data points and the dimensionality of your data, of your data set. Not of your data, yes, let's say the number of samples of your training set and the dimension of your input. So if you do that and you start looking at, let's say, the spectrum of your covariance matrix, and of course you need to go in some thermodynamic limit, because I mean, if you want to have this kind of continuous spectrum, you need to go in some sort of thermodynamic limit. So D goes to infinity and goes to infinity, but they go to infinity in a comparable way, okay? You see that depending on the ratio of the number of samples you have and the dimension and the dimension of your input space, you have that the spectrum changes, and in particular, if t is equal n, you have that the spectrum peaks around 0. So you have 0 eigenvalues there. And what does it mean? It means that, okay, there is still the dagger. Okay, it's -1. Okay, it's the inverse of the covariance matrix, this thing, basically. The inverse of the covariance matrix is going to have super big eigenvalues. And this, of course, means that the variance of your parameters is going to blow up. It's increasing. So your prediction is super sensitive to whatever kind of noise. And if you try to plot the result, so you can actually see a sort of linear peak. There is a linear sort of double descent where in case the dimensionality of your data set is the same as the input parameter space, you just have that the generalization error blows up. But then you may tell me, okay, but then I'm pretty sure this is a scam. It's just that I can rephrase deep learning in some way so that in the end it is a linear regression and the double descent is nothing but this. Is just that we are too ignorant to understand it. And I hope that when I finish this part of the talk, I mean, you will be convinced that this is not the case. But in order to get here, we need to give a look at the double descent phenomenology. first experimental thing we can notice is that if we add label noise to our training, the double descent curve is still there. So you keep on seeing the double descent, but the curve itself is going up and it's moving right. And the way you can interpret this thing is that, of course, the data are becoming noisy. So you cannot really, use noisy data to learn structure, to do, let's say, yes, to learn structure. And then this explains why the curve is moving up. And the reason why it's moving right is that you need to overfit noise too. So it takes a little bit more parameters, right, to do that. End of the story. Other stuff. The double descent is independent of regularization, but if you add regularization, you may have a sort of washout, or it gets mitigated anyway. And by regularization, I mean early stopping techniques or L2 regularization of parameters, whatever, you end up having the same phenomenon. So it's a little bit, it's mitigated. And the same effect can be seen by ensembling, which means I train this, I have my neural network. I train it once, I train it twice, I train it 3 times, and then I start averaging over the various results I'm finding. And also this effect is mitigating double descent. Yep. I think that you really need to average I think you really need to average the curves themselves, or not.
This is not a classification problem.
Yes, I think so. What? I think without regularization. Or I think you need to take all the results together. It's not averaging the curves, but it's putting all the, indeed, the point is the following. It's just like taking many, many, many more points, right? Yep. Yep. Exactly. To me, is the same as enlarging the sample. Exactly. This one.
No, on
the previous
last,
one.
Yeah, previous one. Yeah, sorry. Yeah, but just because there is so each point, of course, you need to. There is like the optimization procedure, like the number of epochs is heightened. So, what is how do you stop? So at each point, so you have a different model.
I think you stop at the same amount of epochs. So at each point is a different model, and then I just say I train. In order to make them comparable, I train every single model for the same amount of epochs.
Is it a good procedure? Because I would say that.
I see your point. It's just that otherwise, how do you do that? Because
the amount, the decreased ratio, for instance, of the loss, because at some point you are training the number of, yeah.
I see, but let's say that I can just say this in their defense. It's not my paper, but I can just say that they checked that all the models were converging. I think that they checked it. So this model, I would say that, okay, let's say that the slope of the loss function, for instance, was nearly 0. Of course, maybe it was not comparable, but anyway, this is the technique they used here.
Yeah.
Okay. The only thing I can tell you is that all these models converged, or you would say that they were that the training was converging, or was all as already converged, but I said. I see your point, but okay. That is something this is more about the bootstrap conjecture. So there they do something in a fair way. I do not know whether, there are other studies that do exactly what you want to do. And I do not know whether we will have time to talk about them in case, okay, whatever. Then we may just ask, indeed, but is this something, is this a transient, is there something that we are missing? So we keep on doing more experiments. And let's say that now we want to see the effect of not only the parameters, but also changing the number of data, right? So here you have here you're changing the training sample, and here you're changing the model size again, and you try to compare the training error and the test error. And something, because I mean, people usually think that if I have more data, then I generalize better, right? I have a model, I feed it with more data, and then I'm expecting to generalize better. And this is actually, I mean, this plot shows you, again, comparing training on the same amount of epochs, right? So caveat. But anyway, it is showing you that this is not for free, because for instance, for medium-sized model, if I increase the amount of data, it's not for free that I get that it gets better. And in particular, you may also find a sort of a so-called sample-wise double descent. So I generalize poorly, then I generalize better, then and so on and so forth. So you find another double descent in this direction. And in particular, you can see that for medium-sized networks, I mean, having more parameters is not really increasing your test error. You're not gaining anything out of this. But the most surprising thing to me is this one, actually, which is, what about if I train longer? I mean, what happens? And so if I have a small network, what happens is just, let's say, I do not have the computational power to reach the interpolation threshold. I cannot reduce the training error to 0. No, or maybe I can, but it doesn't matter. I mean, at some point, I'm not seeing anything strange happening to the test error, sorry, as I train the network more. For intermediate model, I'm seeing something that I actually like. This is what I would have liked to see. So I'm getting better, but then I'm overfitting, so it's getting worse, and this makes sense to me. And for large model, actually, what is happening is that, okay, I'm generalizing better, then I'm generalizing poorly again. I'm generalizing poorly, and then I go down again, and this is super counterintuitive.
But I mean, I think that's, of course, if you're fixing the batch size, I think that the number of weights update must be proportional to the number of weights.
Can you say?
Because you're having a large number means having a large number of weights.
Yep.
And so the number of updates must be proportional to the number of weights of your model.
Yep.
So because if you're fixing the batch size and looking only to the epochs, a larger model requires much more updates because the number of weights are much larger.
True.
So that's why I think that.
Yes, but okay, but this is not explaining this, right? This is explaining what we were seeing before. The fact that I have more parameters, I mean, I do not understand how having more parameters tells me how I should go up and down.
Fixing, yeah, if we fix the number of epochs, we cannot compare.
That is fine. Exactly. So whatever happens here or before, I agree with you. But here, what I'm changing is the number of epochs. So I'm training longer.
Longer, but the number of updates will be exactly the same because the batch size is fixed. But having a large model means having a large number of weights.
Yes.
So to compare in my head, I think that it requires to decrease the batch size for larger models to have a larger number of weights updates.
But yes, but this wouldn't this tell me just that I'm stretching? I mean, for a larger model, I should see the same curve but just stretched. But if I wait forever, this thing is not going down, the green one. I can wait forever and this thing is not going down, and I like it because I mean I like that it doesn't go down because that is the only thing I can actually understand. If you ask me, I would prefer that also this thing doesn't go down. It does, and the point is that. Maybe here I have some statistical property that is just some statistical property. But here there is something dynamical happening. And then I mean, this means, okay, not only look at your problem, but look also at how you search for the solution, right? So this is related to the optimizer. This is related to the data set or the problem itself. And they look the same, and I cannot understand neither of. So I'm not feeling comfortable, right? Yeah. Yes, because you tell me, if you're here, and this is the minimum test error that you're finding, I do not care about the fact that then you're going up and down on this roller coaster, because if this is the minimum, it's another way of overfitting. I mean, I'm overfitting and I'm overfitting more or less, whatever, but I'm still overfitting. It's not always like this. I mean, here I see that you're comfortable with the fact that this point looks higher than this, but it's not always the case. It may be lower. Yeah. No, exactly. It doesn't make sense. But I would have preferred that it was always above the other one, but okay. Okay. How do we understand this? We do not, but we can rely on some sort of simplified model. And in particular, there is this random feature model that helps. And what is it? I mean, what is this? This is a sort of prototype of a two-layer neural network. So this is your input. You have an hidden layer with a nonlinear activation function. And the point is that this is not trainable, okay? So theta here is not trainable. And then you have a linear layer at the end, and the linear layer is trainable. Okay. Exactly, but okay. I can tell you in words also, because otherwise the similarity thing, we're never getting there. But the point is that, why? Because before, with a linear fit, as I said, you had that the maximum number of effective parameters was the same as the dimension of your input, right? This allows you to do two things. The first thing is you are decoupling D and P. So I'm calling P, for instance. Okay, this is my bad. This is not P. Okay, theta, this is a typo, and I think it's my typo, but whatever. Forgive me. P, so the number of parameters is going to be given by the number of hidden nodes you have here. Okay, so you're decoupling the thing. In addition, it doesn't really make sense to talk about initialization if you're doing a linear fit, because no one initializes anything when you do a linear fit. You just have the solution. And I mean, you do not see that kind of stochasticity. Having a non-trainable random thing allows you to see the effects of initialization in some sense that you have in deep learning, and you will never have in linear models. End of the story. So you take a super easy model. This is nothing but, let's say, you have a Gaussian input, and you create sort of linear model. And you train this thing. I mean, you're not even training again. You're just solving this thing using ridge regression, so that you can also see the effects of regularization if you're interested in. And you start looking at the generalization error. And what Dascoli and people in Paris did was to be able to split the contributions of the different contribution that made up the generalization error. And these were, okay, you have a standard Gaussian noise that just comes from the fact that also that your model is a stochastic model. You have a bias term, and that is standard. And then they were able to find that you have a sampling contribution, which comes from the fact that your training sample is finite. You have an initialization term that comes from the fact that you're in random feature models, you're initializing the hidden layer weights randomly. And you have a noise term that takes into account noise in the labels. So that is, you can interpret it as label noise, also in classification, right? But of course, this is a sort of regression. They were able to quantify this. This can be parameterized, of course, in some weird limit. I mean, it's a long way to Tipperary. There is a lot of machinery behind this thing, but I mean, I gave the reference where you can find everything. And this is the final thing. So what I saw is that the two main contributions that lead you to the peak of the double descent behavior in random feature models, which is not deep learning, it's a simpler model, but let's say it's a proxy, are these two. The first is the noise variance. So this is the noise term. So the noise in the labels, if you want. And the other comes from the initialization variance of the hidden layer weights. this is the result with nearly to no regularization. If you regularize it, you see that also this, I mean, the bump is reduced. So this is consistent with what we were seeing before experimentally. Yes.
I don't know if I like properly take the message from those slides. Is this just basically a linear regression on a random feature space?
Yes, you created a machinery in such a way to do a sort of kernel regression, right? I transformed something in a weird space, but I'm not training the space. So the base is fixed, and then I'm doing linear regression.
Okay. So
Yes.
what you are saying to me is that from this setting, so a random kernel and then a linear regression, I have, if I understand correctly, the same behavior that I have in the linear regression model.
Exactly. And this is the reason why we go back to the scam thing. Then this is a scam because these two things are clearly the same thing, just in two different spaces. I will convince you. No, maybe not, but I hope I will briefly.
Okay, thank you.
Triple descent, right? I know that you were waiting for this. It's not double, but triple. Triple descent, sometimes you can see it. And what is this? Because the point is, okay, I couldn't live with a single peak. I cannot live with two. So just to tell me that, I mean, there is the same, I mean, it's all the same thing. It is. In training random feature models, for instance, or simple, super simple neural networks, you can actually end up seeing two peaks. And these two peaks, if you study them, are, I mean, you can identify them to be the linear peak happening at number of sample equal the number of input dimension, and another peak happening at number of samples equal to the number of parameters of my model or hidden layer parameters, whatever. Okay. When do you see both? You see both when the activation function, for instance, in random feature model of the hidden layer is nearly linear. For instance, tan H near the origin is linear, far from the origin is not. But this means that it's, I mean, is linear with a good approximation. I mean, as a non-trivial linear component. Okay. And so if you start plotting what happens, for instance, in the plane P over D and N over D, you start seeing that in absence of noise, signal to noise S and R is signal to noise ratio. In absence of noise, you tend to see, or with a very little noise, you mainly see the N equal P, so the nonlinear peak. If you increase the amount of noise, you actually see both the linear and the nonlinear peak. And then you may tell me, okay, but this is a random feature model. I mean, I see it's a good proxy, but this is not a neural network. They also engineered in this paper a simple setup to train a simple neural network, and they found that the thing is consistent. So you see both peaks also with a simple neural network. And then what are the effects? I mean, and then let's try to use the same tricks we were using before to see what happens to these two peaks. So this is the vanilla model, right? If I perform ensembling, or if I add regularization / early stopping, the only peak which is affected is the nonlinear peak. The linear peak is there. The linear peak disappears if and only if I turn off label noise. So the linear peak is there no matter what, it just depends on noise. The nonlinear peak depends also on training, apparently. So if you regularize or if you do some other stuff, it seems it goes away. In order to convince you, oh, well, okay, fine, this is the same thing as before, just believe me, this whatever. Another way to see this is for the random feature models is the following. There is apparently, I was not aware of this, but apparently there is a way to, I mean, in the end is like you said, this is nothing but a linear regression on on some strange space, right? So in order to see the origin or the spectral origin of the linear peak, before we were looking at the covariance matrix of what? Of X, of the input. Now we look at the covariance matrix of this hidden hidden feature space, whatever. A thing that can be done, apparently, especially in the thermodynamic limit, is to decompose this Z in a linear part and a nonlinear part, where the nonlinear part acts a little bit like noise. It's a little bit strange, but let's say this decomposition, and more details can be found here, allow you to study independently the two spectra, the spectrum of the linear part and the spectrum of the nonlinear part. And this is what they plot here. In particular, the spectrum of the linear part is solid lines, and the spectrum of the nonlinear part is dashed lines. So for instance, if I have a linear activation function, and of course, I only have the linear contribution to the spectrum of the covariance. I mean, I have only the linear contribution to, Z is linear, let's say. And so I will only have the linear spectrum of the covariance matrix, and or the spectrum of the linear part, whatever. I hope you got me. So we see that this is exactly the behavior we were expecting from the linear model slide. And we see that for n equal d, you have that the eigenvalues of the spectrum, the eigenvalues go to 0. I mean, there is a non-negligible fraction of the distribution of the eigenvalues that goes to 0. If you have a nonlinear, only the nonlinear part, so for instance, here the activation function is the absolute value, so it's only nonlinear. What you see is that the spectrum does the same, but at n equal p. And for intermediate activation functions, which are nearly linear, you have, let's say, you put together both behaviors. Just that the linear peak gets regularized a little bit, while the nonlinear peak still has a similar behavior as in the totally nonlinear activation function case. Fine. So more or less, this was the phenomenology I wanted to talk about. But this is true, of course, for simple models, regression, classification tasks, and whatever. Classification and regression are two pretty specific tasks. And classification is also worse, right? Because I have an image, I process it in a very non-linear way. And then, people are used to say this, right? I take the dimension of my last layer is just the same as the number of classes. So whatever thing I get there, I then apply a softmax transformation, which means I'm mapping an R to the n number of classes space onto a simplex. It's something crazy. So nothing tells you that whatever kind of thing applies to regression and classification applies also to similarity, right? So Nayara, have fun, come back. These are your slides. Have fun. Yes.
Oops, can you hear me? Yeah. Sorry. Yeah, so now we are going to move to the second part. Now that you understand everything about double descending classification, of course, right? Then we move to something more complicated. But yeah, indeed, there is, basically just to sum up, it's not for free, right? That what you see there in classification is also going to appear here in contrastive, right? Some kind of comparison with contrastive. But I want to start with some tests, right? Human AI, let's see if you're a human AI. So please have a look at this figure, right? Like on the left, on the right, and explain the partner rule that distinguishes the 6 box on the left from the 6 box to the right. Just look and say it. Just look at it. Not IQ test, don't be afraid. Just like look and say what are like the relations that you can see here that are common to this image that are not common here. Just, I don't know, maybe you're our eyes. You know this, but you just say it. What's common from this, guys? The 6 that are not common from here. Perfect. That's it. So you see on the left, they are all equal, and on the right, they are different by something, by or the size or the shape or the color. Very good, human. Good, very good, very good. This is one of the Bongard tests, right? This computer sciences, he created this like several tests, I guess 100 tests in the 60s. It's kind of a challenge to AI. Just like, and these are, there nowadays, although we have these very fancy networks, there are no AI systems that can solve this type of tests in general, right? I'm saying in general. And this can be, okay, I choose actually something that was quite easy because in general, they are super challenged, right? They are things crazy like this, as crazy like this. And in general, some people actually keep adding more tests in this website, so you can have a look at this website. And they require a rich and general understanding of basic concepts of equal and different. You see, it doesn't matter much how complicated are these features, just the relation among these features. So it's something that's very complex indeed, right? I don't know. No, neuroscientist question. I mean, I don't know. Maybe some neuroscientists can answer. Probably there are neuroscientists here, right? I don't know. No. Yeah, how we do it. I mean, you know, a baby can do this very easy. Ah, I see how well. Yeah, no. Yeah, this kind of tricky, right? This kind of indeed it can be very tricky. I don't know. Good, provocative question. Indeed. So in principle, this requires kind of general understanding of basic concepts of like what different and right, different or equal, right? Something very. How do we explain this, right? I mean, I'm not asking you to classify anything. I'm just saying this is equal or different. Yeah. Sorry? Yeah, indeed. It's easy, of course. Ah, yeah, indeed. I don't know. We have to see and read the rule, right? This, for instance, this one here, you got it, right? Sorry. Now this one is like symmetric, right? You see, this is the. See, human. I mean, you have more than 400 tests. You guys can go there and keep trying, but there are some that are really tricky, right? You have to read the rule, otherwise you don't get it. Yeah, it's not like that easy, indeed. 2 humans here in the room, 2 humans. Yeah, could be. Yeah. But here, okay, just to motivate, I mean, the people not have to solve everything, right? Physicists, right? So why we're looking at this, right? This is basic, right? This is ML foundations. I mean, we're studying here how we learn from contrastive concepts. This is, of course, a fundamental question. And indeed, as I said before, what matters here is not really the features, right? But the relation among the features. That's something else. And even like if you think about applications, this is widely used in machine learning, contrastive learning, and then in principle, self-supervised tasks and this kind of thing. So you can find a lot of applications to this as well. Okay, so now I'm starting to talk about our paper like it's like 1 hour. This is like after 1 hour. Okay, so we're talking about our work properly. We study actually two phenomena in this paper, right? It is online offline correspondence, and that basically when you compare, you just take like a model, then you train a model with just fresh samples, so you don't repeat, you don't keep like many epochs, and then you compare with a model that you have seen many times the same samples, like for several epochs, and you compare, as you said, the batch thing, right? In this case, you compare exactly the same amount of optimizer updates. And then what happens is that in classification, this seems to be valid, but this breaks down for contrastive, is what we observe. But I don't think I have time for this. We can ask us later today, but I'm going to talk about the double descent in the context of contrastive. And just a spoiler, I'm not going to solve these puzzles, right, that I showed at the beginning. We are doing something much simpler here, right? It's just a motivation, a hope that at some point we'll be able to do this. Yeah.
Sorry, the difference between like contrastive.
I guess it'll be clear when I show the architecture and I show the thing. But in principle, I don't have predefined classes. I can have infinite amount of classes here. I'm not saying like how many classes I have. Of course, we are going to use a data set that we understand very well, like MNIST, fashion MNIST, CFAR that we know. But in principle, I'm not giving this information to the network, to the architecture, as Veronica said, right? In principle, for classification, your last layer has like 3. The output is like 10, right? Just the amount of classes for the case of the usual data sets. In our case, it's not clear what would be this bottleneck layer. That's it. I guess it would be clear when I show the architecture, it'll be easier to understand. Okay, so this is the plan. So first I'm going to show the architecture, Siamese neural nets. That's the simplest way that you can do a contrastive learning, a contrastive comparison. Then I'm going to show the setup that we use for training and then the results. Okay, that's it. So this is a Siamese neural net. So they're quite simple neural nets. You see, they're not super, I guess they are older than 10 years. And the idea, what's the idea here? The idea is that I have a copy of 2 neural nets that they share the same weights and biases. And I have 2 outputs, right? Basically, a successful Siamese neural net is trained to see if these 2 outputs has some equivalent relationship. So what's the story? I have like a copy, they are trained together, and I have a bottleneck, and I have some bottleneck layer where I measure the difference. Could be Euclidean distance, could be some more fancy distance. And then the network has to decide if this is equivalent or not. In our case, we're going to use this for images, but this could be anything else. Could be like a Lorentz transformation, for instance, as these guys, these physicists did in this paper here. We can have a 4-vector here. This is a Lorentz transformation, and I'm going to ask the network to see if there is equivalence relation between these 2 inputs and output. And what is the task? Maybe now it would be clear, right? This is a supervised task. I take a data set, I have to construct the pairs, and I'm going to label them, right? With this, our convention is like y equals 1, related, y equals 0, unrelated, and then now it's clear, right? Yeah. And then we can train this with a contrastive law or cosine loss. There are different types of contrastive losses. I will show you. For instance, we use, in particular, the contrastive laws. So what's the idea? With this convention, right? If y equals 1, this term is 0, I want to minimize the distance, right? So what the network is doing in the hidden space is collapsing points that are similar. If it's different, this term is 0. I want to minimize this term, so I want to pull apart things that are different until some margin, right? I don't keep pushing forever, right? Until some margin that okay, my margin is m. If they are distance in the hidden space by a distance that's larger than m, I classify them as different. I put a threshold there. It's very simple. And it's very simple and works super well. That's a kind of surprising also. And then we train, right? We study how training in test errors vary by increasing the network size, because exactly we want to see the double descent. So by increasing the width, I just mean like I'm adding more parameters, right? I'm adding like more nodes in the layer. And we did this with, the MLP here, right? But also with convolution, we use different losses to see if there is an effect of the losses. We also use different data sets. And the most important thing that's kind of obvious, but apparently nobody did before, is that if you have pairs, we can have 2 types of noises. If you have pairs, I can have 2 types of noises. And is what we call single label noise. That's the usual noise, right? Then you have I have the labels here, and I have NEC classes, and then I can just flip this label. So this is some type of noise, that the usual noise that we expect in label noise. But if I have a data set of pairs, I could also have this type of noise, right? I can basically, these things are similar, and there is a noise that they are labeled with different. And this is obviously, this kind of error is going to propagate in a different way in my data set, right? Because this noise appears the same everywhere, right? This mistake is repeated everywhere that this samples appears, this noise is repeated. However, here, this noise is concentrated. So I can already tell you, you can already, using the words that I'm going to use later, there is some kind of transitivity breaking in this case here, right? You see, this is propagating in a way that's, let's say, it's consistent, right? It's a noise, but it's consistent everywhere. And here, no, there is some kind of breaking of consistency. Okay, so let me show you some of the results. Well, the first result, you know, right? Otherwise, we will not have the paper, right? Double descent appears in Siamese neural nets. And just, I'm going to explain which these curves are, but here just repeat again the plot, right? The cartoon. And we see one descent, the second descent. The dark blue is the single label noise. The light blue is pair label noise. The black is just without noise, any type of noise. And I'm going to go over in detail of each of these curves. For example, here I'm training this with 6K. So I have like 6,000 pairs. So you see, if we were like normal people, we stop at the training here, right? We're not keeping adding parameters because I'm started seeing this in principle overfitting, right? I should stop, but then if you have a collaborator with a cluster, you're just keeping adding parameters, and then you will be able to see the second descent. But it's really like, at this point here, I'm already over parameterized. And then you see, you're gonna see the peak just much later, right? Just much later. Another thing that we also saw in this case is the epoch-wise double descent, right? We see not only when we keep increasing, right, the number of parameters per layer, but we also when you keep training for longer, right? I guess someone asked at some point, right? You're training for longer. Here, indeed, right? If you train longer, what would they expect, right? Stop, use early stopping because you start overfitting, but no, if you keep training, actually going better. And you see, I mean, something that Veronica mentioned early, this guy is lower, right, than this best point here. It seems a bit lower. Not. Ah, yeah, indeed, here, right? Yeah, I don't know. I have to go here to see if it's. And then you see that even without noise, you can see this kind of little peak here, right? And as far as we know, in classification, people cannot see this peak. I mean, just in similarity. So for some reason, double descent, epoch-wise double descent is exacerbated for contrastive learning. It's something that's not clear for us yet. Yeah, this result, the archive version is I'm just showing here. So maybe the most important part now is that you see that, of course, I didn't say, but you can see these curves are very different, right? And here, of course, we are putting the same amount of noise. I mean, in the case of this plot, 10% of effective noise. So why I'm putting the same amount of noise and I'm observing like two very different curves, right? This is kind of weird. And okay, let's go step by step. Please, maybe you can stop me at any time. I don't know if you have questions. So here you see that the single label noise test error is higher in this intermediate regime, right? For medium-sized models, like here. And then there is, of course, now this is a super high dimension. I have 10 classes. You can reduce the problem to 2 classes and 2 dimensions to try to understand this. And is what we have here in this great picture by Veronica. So how can we try to understand what's going on here in this region? Let's suppose that I have 2 classes, red and green. And in the case that I have no noise, I just say, okay, if they are separated by a distance d, I classify they as different. If they are closer than d, I classify them as equal. If I'm introducing pair label noise, what I do? I take two guys here in the green class, and I call them different. And I take one red and one green, and I call them equal. So what the neural net has to do to adapt to overfit this mistake, right? Maybe what it can do, just put this guy here, right? And already be good. I already classify as different. And then this guy just put close to each other, already classifying them as equal. I somehow can adjust, I can explain this noise this way. Now, if I have single label noise, what I'm doing, I'm taking a distribution of red and calling the guy inside the green, right? I take a distribution of boots and call the guy inside, a distribution of trousers, and I one sample inside a boot. Somehow the network has to do like magic, right? To adjust to this error. So then we expect, well, maybe that's why this is harder, right? So I have more error for the single label noise. And this was our expectation, right? Before we're doing the experiment, this okay, everything makes sense, right? Okay, this is maybe that's why this is higher. But then you keep training, right? That's the thing. If you have a cluster, this is kind of, although this data set is quite small, this is a heavy experiment because they have a lot of parameters indeed. And then you have to do for many times, right? To have a sample. Yeah. Much later, right? Yeah. Yeah, here you see like the maybe here. Yeah, you see like I'm starting over, I'm over parameterized from this point here, right? You see that the peak is here. So that intuition that we had with the linear model, that's gone. I mean, I don't know. This is actually something that we would like to calculate, right? But it is not easy. Because then, you know, like the practice, if you know how to do this, is amazing, right? You can just say, okay, just train your model here, right? You don't need to keep trying where it's good, where we have good generalization. Okay, so this. Yes, so. And okay, so then, okay, this is what we expect before doing the experiment. And then we saw this, but if you keep training, you see that at some point there is a crossing here, right? You see that the pair label noise is starting, actually is not going down and it crosses, right? And you see, remember again, here I'm training this with 6,000 pairs and I already have like 100,000 parameters. So I'm way above, I mean, super over parameterized. And then you just like, you see that in the deep over parameterized regime, right? The PLN actually, it seems is not getting better, right? It's just, the single label noise is better. So then we said, what's going on? And then we decide to look at the train error, right, of this guy. See, this is the generalization error. And this is the training error. And what we expect here, right? I'm already super over parameterized. Remember the simple examples at the beginning. So in principle, I can memorize my entire data set, right? Remember that memorization. So this is what we see here, right? My training just goes to 0. In principle, I can just memorize my entire data set, but this is not happening here. No matter what we do, it seems this guy doesn't go to 0. But you notice, okay, this is quite small, right? You should look at the numbers also, right? Test here. See here, you see this number is small, but I mean, never goes away, no matter how many parameters you add. And they thought, okay, let's reduce the high dimensions again to a simple problem of 2 classes and try to understand what's going on. And remember what I said a few slides ago, right? Single label noise preserves similarity relations because this error appears everywhere. It seems this pair label noise is kind of breaking some transitivity, right? It seems when I'm introduced this type of error, I'm somehow introduced some inconsistency in my data set. And then there is a way to kind of visualize this for humans, right? So what's going on? Yeah. So let's try to understand what's going on. So let's reduce again this problem to 2 classes and like in much less dimensions. So here I have the black and orange class. And if they are similar, I connect them with a green edge. If they are different, I connect them with a red edge. So if I have no noise, I have this. Okay, no noise, they're connected, they're okay. In case I have single label noise, what happened is that, well, I take one of the samples here that orange and I call it a black. So the network to adjust here could just put this guy in this. I mean, it's doing a mistake, but I can overfit this because I have enough parameters. I can just put this in this class, in this chain here with the black, and it should be fine. However, if I have pair label noise, it's more complicated because if I have pair label noise, what I do? Let's do slowly. I take this guy, right? These guys are different, and I call them equal now. And you see, now I have a transitivity breaking because I cannot overfit this because it's the equal. Now these 2 are different, but I'm calling them equal. So I cannot close this triangle. Can you see the color? There is a gray. So I'm introducing a transitivity break in this gray area here because I cannot, no matter how many parameters I have, this is inconsistent in my data set. Now, let's do one more. These 2 guys are equal and I call them different, right? I'm introducing this error in the pair. And again, I introduce an inconsistent, right? Now it's inconsistent. I cannot close this chain anymore. And then in principle, we call this effect like density-induced break of similarity because no matter how many parameters you add, you have inconsistent in your data set with this type of noise. And indeed, you can even derive a formula for this that perfectly matches this in the asymptotic regime. So it's really like you can really derive and compare with the experiments, you get this. Okay, I'm getting to the finally. So yeah, do you want to say more? What? What do you mean? Say it. I don't know what you want to say. Mm-hmm. Mm-hmm. Let me put.
If those connections are sparse, I cannot even tell the difference, right? Because maybe one image is by training stuff on once. And therefore, I cannot do it from the box. Whether that mistake comes from a single label noise or a pair label noise, an image that is appeared only one, you cannot tell the difference. If you create the pairs in such a way that they are dense.
Yes. Like, hard for them to see this from this picture, but yeah. I guess her point is that here it's very. All these things are connected, right? If I have some skip connections here, it'd be hard to see this effect. But this is in general the way people construct these data sets. They want to use the entire data set. It's really highly dense. What she means is that if, for instance, I don't have connections like this, if I have a data set that's not, this effect is basically, you don't see this effect, right? Because it's not so dense. See, yeah. Okay.
Of neurons, I should expect to be always worst, because it's much more. It's much more difficult to be fitted in a sense by the network, because it has a problem.
Yeah, I understand what you mean. Just like interesting, because that's good, because our intuition was different, right? Our intuition was exactly this, right? That we would expect this. Oops, I show you somewhere. Yeah, this. That would be easier actually to fit, but okay, it's just yeah, this is good.
Why? Maybe why do you think that it's easy?
In this case, in principle, I'm taking this distribution, right? And then I'm calling sample inside the distribution something. It's not a smaller deformation. Just that in the over parameterized regime, let's say deep over parameterized regime, I have so many parameters that I have in principle much more dimensions to escape this somehow, right? So it's in principle, it's easier to do this deformation of the network. But this is like words, I agree. In principle, that's a way to explain. And this way to explain the PLNL, we are pretty sure that's right, because in principle it fits, right? The intuition fits the formula, basically. Right?
Okay.
Yeah, but I agree. No. Exactly. What we can do, right? There is 785 dimensions here, right? 7. Fine. So okay, today we focus on the double descent, right? There is another phenomenon in this paper, right, that we discussed, that this online-offline correspondence. We can discuss later about this, but I don't think we'll have time. Indeed, we will not have time to talk about today. Oh, yeah. Well, okay, that's okay. I think it's okay. We can talk later. I have extra slides, but we can do it later. In any case. Okay, so I hope, right, we stress enough that there is an enormous gap between what we use and what we understand in deep learning, right? I really hope that this is just one case. There are other intriguing and weird stuff. And if you really want to use this for something that you really care about, it's better to understand this better, right? The better we understand these tools a bit better. And indeed, we need a theory, but we don't have a theory right now. So at least we can do something, with these things. And then there are like a lot of things that we can discuss like after the talk, right? We would like to understand why double descent is really exacerbate for similarity. You see, even without noise, we see like a huge peak, and we even like talk with people that work on this, like in the CS community, and they were like amazed that why your peak is so much like stronger than the usual peak, even without noise. Because usually people add noise because, you know, right, if you're exactly at the threshold, right, the interpolation threshold, if you add some noise, you are really, it's very easy to have this jump, right? Because in principle, you should just have the right amount of parameters to fit your data set. But we see this without noise, so it's there. Also, like, you can discuss this for practical applications. We would like, right, to have a hope to be able to derive that interpolation threshold. I really would like to say, okay, n, the same thing that Veronica showed for n equals p, right? The number of parameters equals number of data set. Would be nice to have some derivation also for these complicated models. But of course, this is hard, right? And okay, and then we also saw like some multiple descents, the triple descent that Veronica showed. We also saw in our setup some kind of, the thing goes down and eventually goes up and goes down again. And this is also another effect that we do not explain. I don't know, what you say? Mm-hmm.
Happening at extremely so
Yeah. Mm-hmm. Yeah, I guess that's it. Yeah, thank you very much.
Well,
Mm-hmm.
in my mind,
Mm-hmm.
maybe the number of saddle point increases like gradients to explore properly the loss function and so on and so forth. So
Mm-hmm.
somehow you have this interplay between the complexity of your data, that are there.
Mm-hmm.
Cure the double kind of.
But not for the nonlinear peak, right? You can make it smoother, but it doesn't disappear. That's the thing, right? It doesn't go away. Yeah.
I do find that this is kind of
No, I guess for linear, it's fine, right? I don't know. Maybe you can say, because you talk about this part. It's this, right? For the linear, where was this plot?
I think it's more kind of, I mean, forget about the double descent. It's more about where should you train your model, right? Because if you need to train it in the overparameterized regime, in the deep overparameterized regime, in the end, the main problem to me is that you do not know what's your result, because you do not have a single minimum. You have a huge manifold of possible minima that how are they connected? Because probably, I mean, if the phenomenon you're studying makes some sense, there is a single minimum, or let's say couple, but maybe not an entire manifold that can generalize well, right? So you want to work in that regime, you need to know what the hell you're doing. Or at least, I mean, I was working in theoretical cosmology, right? So I mean, in principle, I can use whatever kind of deep learning tool in the overparameterized regime. At most, I mean, my model tells me that the universe is collapsing and the universe is not, right? But these things are used in real world situations. So you need to know what you are doing. And I do not know at the moment if there is a clear explanation about the time-wise double descent, for instance. And if you work in that regime, I mean, you can forget, you just say, okay, then I'm just working in the overparameterized regime, fine, fair enough. But then if you do not know how is this regularization or self-regularization happening, and that is a dynamical thing that is happening, when do you stop training?
But it,
No. I always think about this horrible example, and maybe it doesn't work. I mean, but this is how I think about it, right? So let's say I want to, I mean, my function is a sigmoid, okay? A sigmoid. And instead of fitting it with a sigmoid, I use a neural network with 10 layers and fulfill with sigmoid functions, right? Yeah, because I'm crazy, basically, right? Because I do not want to think. I do not want to think that the model is a sigmoid. I just want the network to think for me. Let's say it's a single layer, okay? Better said. The best model is the model, to me, the best model is the model that activates only one neuron with the right bias and weight. Okay.
yeah.
Also, because I think that there is this diffusion thing, right? So there is a little bit of noise. So if I say that my sigmoid is 1/2 one sigmoid plus 1/2 the other sigmoid, then maybe, I mean, usually I'm expecting that there is a little bit more noise, so I'm fitting more poorly, okay? So I can take an infinite amount of neurons, but my best model that generalize better is the single solution, or okay, it's a degenerate. In this case, I may activate a single neuron on the line. Exactly. No, indeed.
Exactly.
There is no pre-lunch. No, indeed. Indeed. But let's say that among the various possibilities, I would like to have, some way of detecting one of the. I would like.
Indeed. No, it's no, even like to go back to someone's question about the regularization, right? You understand these things. This is like a pure linear fit, right? I mean, when she showed like the Handel Fourier model, right? It was really like have one layer that's trainable and the other layer was fixed. So that's why in this case, indeed, people can see by adding this effect, they can see like, okay, the peak is getting smoother somehow. In our case, for instance, we doesn't help. If you add regularization, doesn't help at all. The peak is there no matter what you do. Unless your regularization term is so big that you actually don't not see the peak, but just your test here is terrible. You're just going above the peak somehow. But indeed, yeah. Even in this case, people can understand, but only in this super simplified setups. Yeah. I see. Oops. Oh.
You end up with networks that are solutions that are pretty much just as good as any other random restart. So it's not that there's one place you're going to. I totally agree. But you're not getting trapped either in saddle points. And you used to be a few years ago, people would always argue there's all, of course, there's many more saddle points than local minima or local maximum. But that doesn't seem to matter.
Yeah, this is like an impressive plot, right? That's the thing. I guess you should be impressed by this plot. I mean, please take time to appreciate this one. The experimental, because indeed, you see, the training error is 0 and 0 forever. And I'm just adding parameters. And this is lower than my sweet spot. I mean, when the first time I saw this, I thought this cannot be. This is basically this, right? He's saying. Pretty easy to have that data, but they found they're going to find much more complicated equations than find equations. Less they start to impose symmetry. Yes, it's sparse.
But this is, I think, a really important lesson about this is that some people think that they can regularize their way to the physics right? That the cost function can be engineered to help get the physics into the problem as if it were like a prior or something. And I think this is a huge warning to everyone that there's this more implicit regularization going on that can overwhelm your regular, whatever regularization you think you're putting in, because there's a bigger problem the system's solving, which is it's highly over parameterized, and the dynamics, I think it's an interaction of having a lot of weights, which creates a lot of glassy spots, lots of local minima, and on random resets, you always seem as a to end up in year one close enough to descend into it. And that seems to be like an interplay of having a lot of W's and then having the funny backprop dynamics in the space that gets you to one of these. And that regularization is implicitly, it overwhelms any regularization you think you might put in as a physicist to steer the solution somewhere. So that's why I think this is really important to think about.
Yeah. Oops. More questions? Yeah.
People is trying to discriminate, trying to discriminate in order to
It's try to discriminate when looking at various overfitting and etc. between parameters in different layers. So actually deep networks, I mean, not all the weights do the same in a certain sense, and not all the layers do the same, at least for image recognition, there are words that we show at a certain level, they form features, they divide in class, and then
you first learn the edges, then you learn
exactly.
Like the more...
So this seems indication that not all the layers are the same, and indeed it's not the same to do a huge perceptron or whatever, something like that, or add the different depth. Do you know if people has been trying to investigate this kind of different architecture?
This is some question I already got, like people say, why you, instead of just increasing like one by one, like as we're doing, we didn't try this, but this is something that we could like just, instead of increasing, I guess what he's asking is like, instead of, where is this?
If you go beyond this naive picture where you just plot the number of parameters, but you start to say,
but we study convolution also, right?
Yeah,
You also have convolution. I mean, this work we have convolution, and well, I didn't, but we also have the same with convolution, just increasing like the width k some parameter of the convolution. No, we see the same thing. It's actually even better, right, with the convolution, because these are images. What I guess you're saying is like maybe instead of increasing one by one here, I can, I don't know, increase one mode here and increase some number that's different in the other layers. Try to play with something like this. Is what you're saying, or no?
You start looking, let's say, mutual information between first and second layer, the second and third layer, so on and so forth. But then apparently not, I mean, the community is not clearly in favor of the information bottleneck thing. I like it, but other people don't. So I don't know. And I think that this is I mean, that more or less was the approach that was studying what was happening the first and then in the second and then in the
between the layers. Yeah, I see. Yeah,
I think that their approach may be successful in
yes.
Exactly.
Yes. Yeah, because it's clear. If you, of course, if you go very deep and start to look at the filters, it's very complicated. But the first layers, you see exactly what the neural network is speaking, right? If it's just somehow the attention is some part that's very clear in the image. So yeah,
I mean, no, maybe you see that there is the self connection. You know, you're adding the self. I mean, the self connection, right, of neurons with themselves. Maybe you see that the eigenvalues are decreasing as you go deeper and deeper in the network. Maybe you see a pattern. I really do not know.
Would you say this with a CNN?
Yes, we have the same. I mean, I don't have these slides here. Maybe I have this. I'm not sure if. Yeah, it's the same plot. It looks the same. It's a bit better. I mean, the generalization is a bit better because CNN performs a bit better, but we saw the same effect. Yeah, that's.
same object with two different scales, and I say they're either different, or two different objects with different scales, and I say they're the same.
Oh,
That's up to CNNs.
Ah. I see. I see. Yeah, I mean, we did with CNNs. You basically, when I'm saying we did this with CNNs, I just mean we, instead of the branches here, right? Instead of using MLP, we use CNNs for the branches, and they indeed, we also see double descent in this case, and actually performs, if you think about the generalization error, actually performs a bit better CNNs because we have like images, so we expect that. But and yeah. Indeed, you could. No, we didn't. I mean, our noise here is different, right? We're not doing. Okay, I know what I mean. One could do that, but we didn't use data augmentation, rotating, and maybe cutting some parts of the masking. All this stuff. We didn't do it. Yeah, it's another test. One can do it. Yeah.
Self-supervised, you have. I mean, if we want to play with self-supervised, this is
It's exactly
so
this.
that, of course,
Self-supervised.
you look at the one effect at a time, right? So at this point, it's supervised, so it's just transforming zeros and ones and zeros, and that's the thing. And you already see that there is something strange happening. If you start changing also because what you're saying is selecting or like adding noise to the data set, to the X of the data set, to the input itself, right? Yes.
Yeah, exactly. Yeah, this will be, let's say, the semantic, the thing that we want to do, right? Eventually, because this is like for applications, this is a must, right? Someone has to do this at some point, because we believe there is a lot of these mistakes in here in the self-supervised, exactly because of this correlation. Yeah, semantic.